Hello and welcome back to our subject, Computer Organization and Architecture. So our discussion today is about data representation. So basically, data representation includes the discussion in uh, number system, the conversion between bases, for example, a decimal to binary, or a hexadecimal into octal number system. Okay, so those are example of conversion between bases. And then we also include in this data representation the binary arithmetic, no? And of course the binary complement using the twos and ones complement. So those are actually discussion which is under also data representation. Okay, so in today's discussion we focus on character codes. Okay, so one basic example of a character code is the binary coded decimal or BCD. So what we have here is a table representing a binary coded decimal. So for example, if you have 0 in a decimal number, this can be converted into binary equivalent, which is 0000 in 4 bits, no? So how do we convert that? Just a review on what we have discussed previously. So you make a series of 1, say 4 ones in this particular case, kay 4 bits man ang ato ang representation. Okay, so the first number here is 1, and then this one here is 2, and then here is 4, and then 8. Okay, so you find a number. When you add the number, that will be equivalent to the decimal number that you wanted to convert. So for 0, so you make all ones here 0. Okay, so that will be your binary coded decimal equivalent. Okay, so for if you want to convert 3, for example, then you make 8 here 0, because we will not be using 8. The same way 4, we will not be using 4, and then we add 2 and 1, that is equivalent to 3, so we are using 2 and 1, so that means that this is 1 and this is also 1, right? That is why for a decimal number 3, the binary coded decimal equivalent in 4 digit is 0011. Okay, so if you notice that we have 10 separate symbols representing a decimal number. Okay, so from 0 to 9. Then under your digit is your zones. Now zones actually represents the unsigned number and the signed number such as positive or a negative number, no? So the unsigned number is represented by 1111, and the positive number is represented by 1100, and for negative number you have 1101. Okay, so how do we use the binary coded decimal? Okay, so example, represent negative 1265 in 3 bytes using pack BCD. Alright, so if you notice that we have the term here 3 bytes. Now if you notice that 1 byte, okay, 1 byte is equivalent to 8 bits. Okay, That is 8 bits. Okay? So, that means that in this particular table, we have to place 8 bits in every byte. For example, this area here is 1 byte, and this one here is another byte, and this one here is another byte. So you have 3 bytes. So what will be our solution? So the first step is for you to pack the value of the given number. This time, when you pack the value, the signed value here is or will not be included in the packing, no, on the packing value. So okay, so which is, for example, in this case negative, it will not appear in this particular solution, no. So 1 to 1265 will now be represented by, for 5, for example, you have 0, 1, 0, 1. It can be found here in your table. Okay. For 6, you have 0, 1, 1, 0. So you refer into your table. For 2, you have 0, 0, 1, 0. And for 1, you have 0, 0, 0, 1. Okay. So these are the binary equivalent of your 1265 decimal number. Now, if we want to place this in our table here, so the first, since our solution here, the packing value is 1265, that is without the sign, which is a negative sign, no? So the first value, which is 0001, representing a 1, will be placed in the first byte here. Okay, 0001. Now, since 1 byte is equivalent to 8 bits, this is where you will place your unsigned value, which is 1111. Because, why unsigned value? Because in our solution, in the packing value, the negative sign was not included. So that means that this becomes an unsigned value. So we place 1111, which is in your, you can see it in your zone here. The unsigned value is represented by 1111. And then you place here, to make it 8 bits, so you place the value 0001 here. Alright? So 1 byte now is equivalent to 8 bits. The next 8 bits will be this value here, no? The 2 and the 6. And then on the next byte, you write down the value of the 5, in this particular, this one here. And then to make it 8, you place 1101, which is actually, in this case now, we include the negative sign, which is represented by, in this case here under the zone, it is represented by 1101. So you will now have an 8-bit, no? So in other words, the sign in placing the value negative 1 to 1265 in 3 bytes, the sign value is placed on the last byte, okay, or in the low order, whereas the unsigned byte or bits, which is represented by 1111, is placed on the high order. All right, so I hope that it is clear. Now let's have another example, no? Let's say represent positive 79 in 3 bytes using packed BCD. Actually, positive 79 can be represented using 2 bytes, but let's say we represent it with 3 bytes. So in this particular case, if you notice that in our first example, you have 4-digit in decimal numbers. So this one here in our second example, you have only 2 digits. So we can make this 4 also to be placed inside your table here. So you have, instead of 79, you can add 2 more zeros here. Okay. If we are using, of course, 3 bytes. So again, the unsigned value should be placed in the high order. So you have here 1111. Since in the solution, the positive sign is not yet included, so that means that we represent it with an unsigned representation, which is in this case 1111. Okay, to make it 8 bits in 1 byte, so the 0 here will be represented by 0000. So this becomes 8 bits. And then the next table, you have 0000 gyapon, no? This one here. Then you add 7. You include 7 in the second byte. So you have 0111 to make it 8 bits in 1 byte. So why do we add 0 in your 79? Because when you add 0 here in your 79, the 79 value will not be affected. It will still be 79, right? Then the next is 1001 will be placed on the last byte with or together with this time signed value, which is a positive sign, okay, which is now represented with 1100. So this will now be your answer for the example number 2. Now, if the number becomes bigger, let's say for example 10,000 or 200,000 something, that means that we need to increase the number of bytes also to cater the given number. Okay? So again, do not forget that regardless on the number of digits in decimal number which is given, you have to satisfy it by adding bytes here. Instead of 3 bytes, you can add more bytes and see to it that on the high order, the unsigned value 1111 is placed, and on the low order, the signed value is placed, whether it is positive, represented by 1100, or negative, represented by 1101, based on our table here in under the zone. Okay, this one here. Okay, so that is using binary coded decimal. That means that when you type negative 1265, this negative 1265 will be represented by this value here in your computer. So in other words, this will be processed by your central processing unit under your arithmetic logic unit, this particular value in binary form. Okay, so next is the ABCDIC code, or we call it the extended binary coded decimal. So again, this is still binary coded decimal, BCD, but this time it is extended. So EBCDIC means extended binary coded decimal interchange code. Okay, so if you notice that in our table, we have here the zone value and the digit value. Okay, so this one here is the zone value here, this one, and the digit value is this one here. Okay, so this is the digit value. Okay, so the binary numbers here, these are the digit values. Now, this one here are the abbreviations. The meaning of the abbreviations here in our table. For example, STX. What does it mean? The start of text. Where is STX? Okay, so we locate it here in your table. STX, where is it? There. So STX, the binary code equivalent of STX is in zone. You have 0, 0, 0, 0. And then in digit, you have 0, 0, 1, 1. So you combine the two, the zone and the digit. So STX, therefore, is equivalent to 0, 0, 0, 0, 0, 0, 1, 0. That is the binary equivalent of the word, the abbreviation STX. Okay? So let's have an example. Let's say, what is the ABCDIC of the word ask? Okay? So we want to represent the word ask in binary form using ABCDIC or ABCDIC code. Okay? So for letter A, for example, A, where's A here? This one. Okay? So the zone value of A is 1100. This one here. 1100. Okay? And then the digit value is 0001. Okay, this one here, 000. In other words, the intersection of A is 1100, which is the zone value, and 0001, which is the digit value. So this A now will be represented by this particular binary code. So when you type A in your keyboard, okay, this A here will be decoded by your or the letter A here will be coded by your control unit, which is equivalent to 11000001, and this will be processed in your logic or the arithmetic logic unit. Okay, and then before it will be saved, and then before it passes through the output terminal, the output of your computer system, which is your monitor, it will be decoded again by your control unit. That is why what will appear at the output of your monitor or at output device of your computer system, such as your monitor, will be letter A. Okay? But what is being processed inside your computer is this particular binary code. Right? Then letter S. Small letter S. Where is small letter S? Okay, this one. Right? Okay, that is small letter S. So the zone value is 1010 and the digit value is 0010. So this is your coded binary number. Okay, then for letter K, we have this one. For letter K, this one. Okay, so the zone value is 1001 and the digit value is 0010. So again, this will be the binary equivalent, the binary code equivalent of letter K using ABCDIC. And this will be processed in your computer. And once decoded by your control unit again, then the letter K will appear in your output device, which is your monitor. So, as a complete word, so what will appear in your monitor will be the word ask. Okay? That is how ABCDIC is being used in coding a particular number or a character. Okay, so we have here numbers also. You have 0. Okay, then the zone value is 11111, and then the coded value, the digit value is 0000. Okay, so very similar to binary coded decimal. And this one here are your special characters. Okay, so there is also the zone value here and the digit value equivalent. Okay, so that is how ABCDIC is being used in your computer system as your computer code. Okay, so another character code which is being used in your computer is the ASCII code, no? Or we call it the American Standard Code for Information Interchange. Okay, so we have here the table for your ASCII code. Okay, so the characters here or the abbreviations here can be represented or can be interpreted by this table here. Okay, now if you notice that instead of having a binary numbers on the left side of your characters, you have decimal numbers. So in other words, if you have a particular character to be written into your computer, the decimal equivalent of that particular character will have to be converted using your control unit into its binary equivalent. Okay, so for example, letter S here, which has a decimal equivalent of 83, then 83 here in decimal number will have to be converted into its binary equivalent. Okay, so let's have a very specific example. Okay, so let's say, what is the ASCII code for the word ask? So the same word with that of our example in ABCDIC, no? So for letter A, for example, if you look at the table, capital letter A is represented by decimal number 65. Okay? So 65 here will have to be converted into its binary form. So we make use of this equivalency in decimal. So we find a number here that we will be going to use to make a total of 65. For example, you have 64 here. You have, by the way, this is 1, 2, 4, 8, 16, 32, 64. We have only 7 bits, no? But what is written here is 8 bits. I will explain that later. Now, so let's find 65 in this particular representation. So you make use of 64, so you have 1, and then you add 1 here, so it becomes 65. So the representation therefore will be 1, 0, 0, 0, 0, 0, 1. And that is this particular value. Now, where did we get this 0 here? This is what we call the parity. Okay, so what is parity? Parity is the most basic of all error detection schemes. Parity is determined by counting the number of ones in the binary conversion. No? Counting the number of ones here in the binary conversion. If it is even number of ones, then it is even parity. So you add 0 on the most significant bit. If odd number of ones, then it is odd parity. You add 1 on the most significant bit. So in this particular case, in letter A, once we converted it into the 65 equivalent of A, once converted into binary equivalent, this will be the result. And if you notice that there are two ones, so that means that it is an even parity. So when you say even parity, that means that we add 0 on the most significant bit of the number form. Alright? So that is why the letter A can be represented by this particular binary coded number. Alright? So you have A therefore is equivalent to 0, 1, 0, 0, 0, 0, 0, 1. And this will be processed by your arithmetic logic unit. No? So when you type A again, this binary equivalent will be processed in your arithmetic logic unit. Okay? Then it will be saved in your memory using the registers, and then it will be transmitted into your output device such as your monitor. And after decoding, after it is being decoded by your control unit, what will appear in your output device such as your monitor is letter A, representing 0100000001 in binary form. Alright? So for letter S, for example, S here is small letter s is represented by number 115. This one here. No? So 115. So we make use of again this conversion method. So the converted value is 11110001. Now if you count the number of ones here, 1, 2, 3, 4, that is even. So even parity. So we add 0 on the most significant bit of the number form. Okay? And then for letter K, we have here 107. Okay? So that means that 107, once converted into binary, is this particular value. Then we count the number of ones. You have 1, 2, 3, 4 again. It is an even number. So it is an even parity. So we add 0 on the most significant bit. So this will now be your representation, binary representation into your computer system. And what will appear in your monitor is the word ask. Okay? So for example, if we will type letter C, say capital letter C, what is this equivalent to? That is, where's letter C here? 67. Okay? So if we will convert 67 into its binary, so you have here 64, you make use of 64. Then 32 cannot be used, so 0. 16, again 0. 64 is what? 67 is what? 64 plus 3, right? Is 67. So you make this 1, and this is also 1. So the rest is 0. Okay? So you have 1, 2, 3, 4, 5, 6, 7. Alright? Then we count the number of ones. You have 1, 2, 3. So that is an odd parity. So we add 1 on the most significant bit. And that will be the representation of capital letter C in your computer system. Okay? So I hope that you understand our character code representation in our computer system using the BCD, using the ABCDI, and using the ASCII code character code representation.